In this video series that I have titled Directional Well Planning Overview, I will review the background material that you need to know in order to do directional planning, and then I will describe the process by which we can do directional well planning for both a single well target and multiple well targets. My name is George Armistead. My contact information is listed there on the front sheet of the notes. The link to the notes is also there listed on the front sheet for your information. I highly recommend that you print the notes out and follow along on a printed out set of notes in order to watch this video. It will be much better experience for you, I believe. In doing this video, I'm only going to describe the process for planning wells and give examples in a single plane. Three-dimensional wells can also be done without the use of software, but the mathematics gets a little bit more messy and it's easy to make mathematical mistakes. So for simplicity, I'm only going to show examples that are lined up in a single plane. And then I'm also not going to describe some of the other aspects that go along with directional drilling, like mud motors and stages of motors and torque and drag and other things. They're important, but they're just kind of outside the scope of what can easily be covered in this video. These are the list of the topics that I'm going to cover in this video series on directional well planning overview. I'm going to talk about some of the limitations of directional planning and doing directional work. We're going to examine the basic directional planning equations and concepts that are listed there for you. We're going to also evaluate the analysis and the planning steps required to do a single target application. And there can be two types of single target application. One is the calculation of a kickoff point when the build rate and inclination have been selected. And then the second case would be the determination of an inclination if the kickoff point and build rate has been selected. Both of those are quite common applications that we do. And then lastly, I'm going to explore and describe the analysis and the planning steps for a multi-target directional application. And we will come up with a directional strategy that meets the required directional plan to hit multiple targets. Now, there are directional limitations and concerns, and I've kind of highlighted it here. The three major concerns I'd like to bring your attention to. First one is the buildup rate. Now, that's the term that we typically use in oil and gas industry about making inclination and azimuth changes as buildup rates or dog legs. But the reality of it is the buildup rate, it actually may be building an angle or dropping angle or turning angle. So it gets to be a little bit confusing, but we do have to pay attention to buildup rates. So there is a limitation. If you drill pipe is more limber than casing is, so we actually could drill a well and have a higher dog leg or buildup rate in drilling a well, but the casing has a larger OD, and it takes more force to bend a larger OD casing, and you would have difficulty running the casing in a well if the angle is too high. Now, just in general, there I've listed for a well that's, say, greater than 15,000 foot TBD, we generally limit our buildup rates or dog legs or whatever you want to call it to 4 degrees normally. And then for shallower wells, say maybe less than 12,000 foot TBD, we may use build rates of up to 15 degrees, depending on how much of a well bore you have beyond a dog leg that you created in your well. So hang down weight, which is the amount of hole section and weight, drill pipe weight that you have below a dog leg makes an important difference. So high buildup rates do increase wellbore side loads, torque and drag, and casing wear. So you have to be aware of that. We also can have difficult hole sections. Difficult hole sections could be from basically because of geology. You could have borehole instability sections. You could be very abrasive, very hard with lots of vibrations. It could be so hard that the bit actually just cannot dig into the rock on the side. Makes it very difficult. So generally speaking, when we have these areas that's based on experience, you'll do the directional work either above or below. I call it these difficult hole sections, and it's generally known based on the experience of an area. And then lastly, hole tortuosity. We have to drill a usable wellbore in which the required casing or completion equipment can easily be deployed in a wellbore. It does no good to drill a well, I call it with drill pipe, and not have any problem, but then you go to run your casing and you can't get your casing down in a wellbore that you've just drilled. So I have included the link on a video series that I put on YouTube on hole tortuosity. I strongly encourage, if you've ever had a problem running casing in a well, or you think you might, I would strongly encourage you to watch the video about hole tortuosity and make sure you manage and mitigate hole tortuosity on your wells as you drill them, so that you don't have any problems running your casing and completion equipment in a well. The object is to have a smooth wellbore. You may have, I call it directional changes in the wellbore, but you want them to be smooth and not abrupt. That would prevent you from having a usable wellbore. The next section that we're going to review, we're going to talk about depth references and coordinate systems. So when we're talking about depth, we're talking about, I call it vertical distances that we use in drilling wells and planning wells. And then in the coordinate systems, we're talking about horizontal distances that we use based off of a grid system for the location of our either surface location or targets that we want to drill. The first one we will look at is vertical depths. All geological mapping and targets are developed from base maps that are always done and based on subsea depths. They need a reference system that's consistent, that doesn't change. So the geologist typically will do all of his technical work and come up with target depths based on subsea depths. Now these target depths, which are based on subsea depths, must be changed to a project depth. And so, for instance, on an offshore location, we're going to have the rig floor elevation that's going to be at some height above mean sea level. So like I say, the geologist describes his target TVD subsea, which is below sea level. So we have to adjust that depth to a depth that's going to be our depth for our particular rig operation. So our particular rig operation is going to have some RKB, which is the distance from the rig floor to the ocean level or to mean sea level. And so we would have to add the RKB to the target true vertical depth subsea in order to come up with our project TVD depth. Another very important distance, I would call it, it would be the RKB to the mudline distance, which is going to be important because in general, we can't do directional work until to some depth below the mudline. The only exception to that I'm aware of is when we use curved conductors in our jacket construction, that allows us to maybe have somewhere between 0 and 10 degrees at the mud line because we have curved conductors installed in our jacket when it was built. So the TBD subsea of the project doesn't change, but the rig floor elevation based on different rig types will change. So generally speaking, the geological work may have been done a year or even more than a year in advance of the rig showing up on location. So we have to take that depth and adjust it for our RKB because it could be drilled with a jackup, a platform rig, submersible, semi-submersible, drill ship tender. There are many different types of offshore operated rigs that we would have to adjust that to our project depth. And then likewise for the vertical depth references on a land operation, typically speaking, land operation doesn't have any sea level on it. We don't see a sea level on it. So we have to adjust it. We're going to have a rig floor elevation that for RKB may be described the distance from the rig floor to the ground elevation. And then our ground elevation in itself is going to be a distance above sea level. So sea level, we can't see a sea level on a land location, but we know it's down below us somewhere. And so, but all the mapping is done target TBD subsea below sea level, and then we have to adjust our project elevation target TBDs by adding the distance TBD subsea to the above sea level distance between the sea level and the ground elevation, and then I add our RKB, which is our distance from the rig floor to the ground elevation. Quite often when we start a project and we haven't even built a location yet, we have no idea exactly what our ground elevation is going to be once you have leveled out on the side of a hill to build a land location. And we may not even exactly know the particular rig that we're going to utilize, what the distance is from the rig floor to the ground. We'll have approximate distances for these, but not exact. So you really won't fine tune this till you actually are probably moving the rig on location to adjust that target TBD to the project TBD based on your actual elevations. Now, horizontal references are extremely important as well. The most important concept is that everybody is working with the same grid system. So land ownership has always been a huge part of human history. Human history has always been very important to control land, whether it was land for hunting, or in our business, oil and gas exploration and exploitation. It's always been very important for land ownership. And so there's always been grid systems, even if you go back to any civilization, the Babylonian civilization, Egyptian civilization, land ownership has always been very important. And there have always been grid systems created in which land can be exchanged, and it's well understood where the boundaries are for the land. And we're going to look at that with just a couple of examples. So here's an example of a target that was given for a well, in which this one happens to be in the U.S., in which you have township and range. And I I made up an example with 5 sections of land: section 5, section 6, section 7, section 8. Now, each section is 640 acres of land, and the size would be 5,280 feet. And so I chose a surface location in section 6 that was 2,900 feet from the north line and 2,800 feet from the west line. And the target is located down in section 8, and it is 2,200 feet from the east line and 2,700 feet from the south line. Now, obviously, looking at this picture, we need to get these distances from the surface location to the east line and from the distances from the target from the west side of this line. So we can, since we have all the information we need on this drawing, and actually in order to calculate these other figures, we can take that and subtract 5,280 minus these distances, and we'll get our corresponding distances on our chart. And then we can visually see that in order to go from this surface location to this target, we're going to have to go the combination of both the 2,480 feet plus the 3,080 feet to get our distance east, and that would be this number here. So our target is 5,560 feet east of the surface location, and likewise we do the same thing in the north-south coordinate system, and we add the 2,380 plus the 2,580, and we get the target is located 4,960 feet south of the surface location. Of course, we would never drill a well due east and due south, and likely, so we would drill a well straight from the surface location toward the target, most likely, and that displacement, by using basic trigonometry, is going to be the square root of the sum of the squares. So it's going to be the square root of the eastern and the southern components of direction, and that's going to give us a distance of 7,450 feet approximately. Now we can also calculate this angle here. So it's 4,960 feet south, and it's 5,560 feet east, and we can calculate this enclosed angle here by taking the arctangent of this distance divided by this distance, and that will give us an angle here, or direction, of south 48.3 degrees east. So this is the direction this well would be headed, would be south 48.3 degrees east. Now, in today's, I call it world of oil and gas, we typically just use azimuth. Now, azimuth, I'm going to show this later, is described in an angle clockwise from due north, from 0 to 360 degrees. So for this case, we know that this angle plus this angle has to equal 180 degrees. So this angle here, looking at the diagram, would be 180 minus this directional angle down here of 48.3 degrees. So our azimuth would be an azimuth of 131.7 degrees. Now, inclination and directional references. Inclination in our oil and gas sector is always measured from the vertical, not horizontal. So a vertically drilled well has an inclination of 0 degrees, and a horizontally drilled well has an inclination of 90 degrees while it's being drilled horizontally. You know, inclination in the oil and gas business is different than what we experience when we drive and we see a road sign, you know, expressing an inclination. I call it if you're driving on a highway, inclination is typically measured from the horizontal, but we measure our inclinations from vertical, as this diagram shows here on the bottom. Now, direction and azimuth, as I've said, azimuth is the direction of the well measured in degrees clockwise from due north, 0 degrees to 360 degrees. So a well heading due east would have an azimuth of 90 degrees. A well course headed due south would be 180 degrees azimuth, and a well that's going due west would have a heading of 270 degrees. So this same convention, as far as I know, is used worldwide almost by all industries, even airline, ships, transportation use this same convention for direction. Now, it's just an interesting note that one of the greatest inventions of all time is the magnetic compass, which we still utilize greatly in the oil and gas business in order to maintain our direction while we're doing directional work. Now, the Earth spinning on a north-south axis makes the diameter of the Earth larger on the plane of the equator than in a north-south direction. So the Earth is elliptical in shape, as this diagram shows here. Now, the center of the Earth is made up mostly of a big molten iron mass. Now, the centrifugal acceleration of the Earth spinning makes this elliptical in shape too, which affects the magnetic field that's around the Earth. And so the fact that the Earth is elliptical in shape and this iron core is elliptical in shape is what creates the properties of the magnetic field such that a compass can easily work. So that's just an interesting note that you might be interested in. Now, inclination and azimuth changes when a wellbore are always made consist of some arc, which is part of a circle with a radius of r. So I've drawn a circle here down in the ground, and it has a radius on it. Okay, so the directional tools are set up at the surface such that it is going to drill some circle either with a large radius or small radius. I mean, relative, that's kind of a relative term. But we can derive the radius of the circle, that's the arc that we're creating, by just using a couple of, I call it basic equations that we learned in high school, and then also the, I call it the equation that we use in terms of build rate. So we learned in high school that the circumference of a circle is 2 pi r. So we know that's true statement. And if we happen to drill a well down into the earth and we wanted to drill an entire circle in the earth, of course, an entire circle would be 360 degrees. So that circle would be 360 degrees times 100 feet for for whatever our build rate change is. So that would take, if we happen to be building at a build rate of 1 degree, then it would take 36,000 feet, 360 times 100, in order to drill an entire circle. So we can set these two equations equal to each other, since they both equal the circumference of a circle. And then when we go through this, we get the fact that the radius of our circle that we're going to need is going to be 5,730 divided by the build rate. And likewise, we can rearrange that to say that build rate is equal to 5730 divided by the radius. So if we have either build rate or radius, we can calculate the other value. Now, it's very important, especially people in the secular world, they'll talk about the oil and gas industry of drilling down in the ground and then drilling sideways. Well, that's kind of a myth, that we don't really drill a well down into the ground to some depth, let's just say 9,000 feet, and then instantaneously start drilling horizontal. That, for all practical purposes, never happens. Even if we were to use a 10-degree build rate, let's just say if we put a 10-degree build rate into this equation, you could divide 10 into 5730, and you would see that it would almost take 600 feet in order to go from vertical to horizontal. So this distance from the kickoff point that you started drilling, building angle at 10 degrees per 100 feet to the point that you got horizontal would be, your radius would be 600 feet. So that distance from here to the bottom of your circle arc would be 600 feet. So you would have to kick off at least 600 feet above your target depth that you wanted to be horizontally in. So you can use this to plan kickoff depths for those type of applications. Now here are the basic equations that we use for doing, I call it making inclination angle changes in doing our directional work. So here's just a section of a arc here that's been created in a well where you have two angle changes. So it has a distance V, which is the vertical distance that takes place while you're changing angle. And it also has the D, the displacement that takes place while you're changing inclinations. And it also has the length that you would drill while you're doing that. And so you're gonna, anytime you're doing that, you're gonna have two different angles. You're gonna have an angle that you started this angle change, and you're gonna have an inclination at the end once you've completed making your angle changes. So R, as we have already seen, is 5,730 divided by the build rate. And this enclosed angle is the difference between the two inclinations. So if this happens to be 30 degrees and that was 60 degrees, then the difference is 30 degrees. It would take a 30-degree change there in order to change these two angles accordingly. Now the vertical distance here can be calculated by multiplying R, the radius there, times the differences of the sine of these two angles. And then the displacement can be calculated by R times the differences of the cosine of the two angles. Now to make the math work out, we generally use a positive R value radius if we're building angle, and we use a negative R value if we're dropping angle. And then you can see that for calculating vertical distance, you use the second inclination minus the first inclination. If you're calculating displacement, you subtract the cosine of the first angle minus the cosine of the second angle. No matter what, if you flip-flop the way you do this mathematics and take the absolute value of it, you will get the correct distance. You know, there is no such thing as a negative distance per se. So that's the way you'll calculate your values for your vertical distance and your displacement while you're changing your angle. Now, likewise, we can take this equation that we saw here, the change, this vertical depth, or change in vertical depth, if you want to think of it that way, can be R times the differences of the sine. We can take that and then we can rearrange it and substitute for R. We can put R is equal to 5730 divided by the build rate into this R here. So if we do that, we end up with this equation here. Now, once we've done that, then we can bring B to the left-hand side of the equation and bring delta V to the right-hand side of the equation, and then we'll get this equation. So, okay, so then we can rewrite that. This delta V is the change in the TBD. So then we have taken this equation and put it in a form such that we can calculate the build rate necessary to go between, to either build or drop between two targets when we know what the inclinations are at the two targets and we know the change in TBD between the two targets. So here's an application example, the first one we'll do in this series. So we have target number 3, we have target number 4, and target number 5. Well, you can see on this diagram, if we're located at target number 3, and we have target number 4 and target number 5, when we get to target number 4, we want to have 46 degrees, so we will be aligned to just drill straight from target number 4 to target number 5. So it's planned to hit target number 3 at an inclination of 32 degrees and build at a 2 degree per 100 degree build rate between target number 3 and target number 4, hitting target number 4 at a 46 degree inclination to go to the target number 5 downhole. It says, due to multiple factors during the actual execution of the drilling of the well, target number 3 is hit with an inclination of 26 degrees instead of the intended 32 degrees. Now that target number 3 has been hit at an inclination of 26 degrees, what buildup rate needs to be utilized between target number 3 and target number 4 in order to have 46 degrees at target number 4 when we hit it? I would encourage you to pause the video and take a moment and calculate your buildup rate using this equation. Okay, well, if you stopped and calculated a value, you would see that if you just plug into the equation that was shown, the build rate is 5730 times the differences in the sine of the two angles divided by the change in TVD. And so for this example, our build rate that we need is 5730 times the sine of 46 degrees, which is what we need at the target number 4. And then we have 26 degrees at target number 3. So therefore, the change in TVD is the same. There's no difference, it's 543 feet. If we put these values in, we need about 3 degree change. And just for fun of it, if you have put 32 degrees in here, which was planned, you would get 2 degrees. But since we are behind on the angle, we're going to need to build at a higher build rate in order to go from 26 degrees to 46 degrees in the same amount of real estate, I would call it. And then here's just a basic triangle with the trigonometric relationships that you need to know about the fact that, you know, the hypotenuse is the sum of the square root of the sum of the squares of the other two sides, which is the vertical distance, and the change in displacement. And then the displacement is the length of the hypotenuse, so that this would be the side, the drill depth, times the sine of this interior angle, and the vertical depth is the length times the cosine of this interior angle, and then of course the displacement divided by the vertical depth is the tangent of that angle. So that's just a basic triangle relationship that we should all be aware of and know. I'm going to describe now the angle property relationships for the tangents to a chord on a circle. So this is, I have taught drilling engineering and well planning and directional drilling on multiple occasions, and this is a concept that surprisingly many people just don't know or haven't thought about, I guess. I'm sure it was taught in high school geometry back a long time ago, but people don't use it every day or don't think about it, and so therefore they just have forgot this concept. But it is very important in order for us to do directional planning. So what I've shown here are 3 different targets on a circle. Target number 1, a target number 2, and a target number 3. So since we have target number 2 and target number 3 that are aligned at some inclination here, let's just say that was a 40-degree inclination between target number 2 and target number 3, you can look at this diagram and see that we're going to have to do something between target number 1 and target number 2, such that when we get to target number 2, we have a 40-degree inclination to just maintain that 40 degrees on down through target number 3. Well, let's just say for the fun of it that target number, the inclination of this chord between target number 1 and target number 2 is 30 degrees. Let's just say that's 30 degrees, and this angle is 40 degrees, then this interior angle would have to be 10 degrees. Now, if you, just by the properties of a circle, since this angle is 10 degrees and you redraw this, I call it this diagram, you'll realize that these two interior angles here have to be 10 degrees also. So what this means is this angle beta here is 2 times the tangent, the difference between the tangent angle and the chord angle at the bottom. So if this happens to be 10 degrees, then it's going to take a 20-degree inclination change between target number 1 and target number 2 to be aligned. So for this example, if we take 40 degrees minus 2 times 10, which is 20 degrees, we would need to hit target number 1 at a 20-degree inclination. So we would have to hit target number 1 at 20 degrees, and then we would have a 20-degree increase between target number 1 and target number 2. We would go right through target number 2. We would have 40 degrees and be lined up to go down through target number 3. Now, another way to think about this same, I call it problem or issue, is that the inclinations of target number 1 and target number 2, since it's a continuous change in inclination, that the average of these 2 angles has to equal the inclination of the chord. So I've said that the chord inclination, this angle, is 30 degrees. So if it's 30 degrees, this angle is 40 degrees, and we just calculated, have shown that this would have been a 20-degree angle. So 20 degrees plus 40 degrees is 60, divided by 2, which is an average, is 30 degrees, which gives us the inclination of the chord. So either way you think about this or you draw this diagram, you can come up with these 2 angles on each end. I call it the tangent angles on each end of a chord when you have the situation where you've got to either do an increase in angle like this one shows, or a decrease in angle to hit another target on your project well planning.